Welcome back to our Chem 152 video series. Previously, we went through how to find standard reduction potential of a galvanic cell. Now we're going to use that galvanic cell and the Nernst equation to find the cell potential. In the previous video, we found a reduction potential for the system 2Ag plus cadmium yields 2Ag plus cadmium 2 plus. We found the standard reduction potential was 1.203 volts. However, this standard reduction potential is only good at 1 molarity. So in this problem we have different molarity, and now we're going to have to adjust to find the cell potential with those concentrations that are not 1 molar. To do this, we're going to use the Nernst equation. The E on the left side of the Nernst equation is the new cell potential. The E standard on the right side of the equation is going to be the standard potential. The N is going to be the number of electrons that have exchanged hands. And the Q is the reaction coordinate, or also known as the products over the reactants. In the previous video about galvanic cells, we already found the E standard was 1.203 volts. Our goal is going to be to find the new cell potential, which is unknown. To find the number of electrons that have exchanged hands, we can look at the cadmium. The cadmium has Cd yielding Cd2 plus. The charge has changed by 2. Therefore, we can conclude that the number of electrons that changed hands is also 2. If we inspect the silver as well, we can see that silver has changed from positive 1 down to 0, which is a change of 1 electron times 2 pieces, and so we would also get an answer of 2 if we used the silver to do this calculation as well. It doesn't make much difference which one you would use. Whatever makes sense to you here is fine. Now let's find our Q. Our Q will be our products over our reactants. In our reaction above, we have 2 pieces of silver, but that silver is not charged. When we write this, we say silver with no charge raised to the second power times cadmium 2 plus with no coefficient, so we don't need to write a power. On the bottom, which is our reactants, we will have silver plus squared multiplied by cadmium, which has no charge and a coefficient of 1, so we don't have to write a power. But remember that pure solids, that is, things that don't have a charge, are not going to contribute to Q. We must remember to cross out the pure solids, which means our silver that has no charge is canceled. The cadmium that has no charge is also canceled. And we're going to write that we'll have cadmium 2 plus on top, silver plus squared on the bottom. Now on the top, our cadmium 2 plus is 0.010, and the silver is 0.100 squared. Whatever this is, this will be our value for Q. Therefore, we will check Q off, and now we know all of the unknowns on the right side of the equation, and we can solve for E. So now we'll place our numbers into the equation. We'll say that E is equal to 1.203 minus 0.0592 divided by N, which is 2, multiplied by log of this fraction. If we simplify this fraction in a calculator, we'll get the number 1, so we'll have log of 1. Somewhat unusually, when we throw this number into a calculator, we'll end up with a cell potential of 1.203 once again. This will generally happen anytime Q is equal to 1. You'll have an E that is the same as the E standard. However, getting a Q that is exactly 1 tends to be fairly unusual. Here's a variation on this problem. You may also be asked for the delta G standard value for the reaction as well. You can find this based purely on the E standard that we have, 1.203 volts, and the N value which we had, which is 2 electrons. The equation says delta G standard is equal to negative N times F times E standard. We already have N and E standard from the previous steps. F stands for Faraday's constant. Faraday's constant is always the same number. It is 96,485. We'll place this in the F slot in our delta G standard equation and now place all of the numbers in their positions. 2 times 96485 times 1.203 volts. We'll multiply all of them together to get the delta G standard. If we multiply these numbers together, we'll end up with negative 232,143 joules. This will be our delta G standard for the reaction above. Now that we know the delta G standard, we can find the equilibrium constant K. The equation we can use is that the equilibrium constant K is equal to lowercase e raised to the power of negative delta G standard divided by a new parentheses that contains R and T. The R we want to use for this will be 8.314 joules per mole Kelvin. And the T we'll use is 25 degrees Celsius, which we change to Kelvin, giving us 298.15 Kelvin. This means that we know the delta G standard, we know the R, and we know the T, and now we can solve for K. Therefore, we plug all the numbers in, and we'll have lowercase e raised to positive 232,143. Note that the negative in the equation and the negative in the delta G standard will cancel out and give us a positive number on top now, divided by R times T. On the bottom, we'll have 8.314 multiply 298.15. We'll punch all of this into a calculator. The K value that we'll get will be 4.7 times 10 to the 40th power. Don't be too surprised if you get extremely high or extremely low K values when you do this calculation. Even 1 volt worth of potential can give you a massive, massive equilibrium constant. Thank you for watching, and we'll see you again soon.